Hello everyone, in this video we are going to present various deadlock and concurrency algorithms. The list of the algorithms that we have implemented includes Banker's algorithm, lock variable, test set lock, turn variable, Paterson's algorithm, binary semaphore, counting semaphore, producer and consumer, and landing philosopher's problem. Now let us dive into each of the algorithms. First, Banker's algorithm. It is a resource allocation algorithm and deadlock avoidance algorithm that tests for safety by simulating the allocation for predetermined maximum possible amounts of all resources and making decision whether allocation should be allowed or not. In this algorithm, the user will first have to input the maximum number of processes and resources to be taken into consideration. Next, the user will be asked to enter the number of resources allocated and the maximum number of resources that the process requires to complete its execution. The user finally enters the number of available resources and presses the submit button to start the algorithm. The algorithm first checks if the request made by a process for a resource is less than the need of the resource by the process. Next, it checks if the request made by a process for a resource is less than the maximum available resources in the system. If both the condition holds true, then the resources are allocated to the process. Otherwise, the process enters the waiting queue. After the process completes its execution, it frees up all the allocated resources and then wakes up the process in waiting list to complete its execution. This algorithm checks for the available resources in two loops, thus making its worst case complexity as n square. Second, lock variable. It provides the simplest synchronization mechanism for processes. It is a software mechanism implemented in user mode. It is a busy waiting solution that keeps CPU busy even when it is technically waiting. The user will first have to enter the number of processes they want to consider, then click the start button. Here, initially the value of lock variable is set to 0. When a process is clicked, it enters the entry section where it first checks the lock variable. If the lock variable is 0, it indicates that a critical section is vacant and the process can enter the critical section. But if the value of lock variable is 1, it indicates that the critical section is occupied and thus the process is sent to the waiting queue, where it waits for the other process to complete the critical section. If the value of the lock variable is 0, then the process sets the lock variable to 1 and enters the critical section. On completing the task in critical section, the process then enters the exit section and sets the value of lock variable to 0. The process in the waiting queue is then invoked back and the whole process is repeated again. Third, test set lock. This mechanism is a hardware solution to the synchronization problem. It ensures mutual exclusion and progress. The user will first have to enter the number of resources they want to consider, then click on the start button. This algorithm is a modified form of lock variable. Here, initially, the value of lock variable is set to 0. When a process is clicked, it enters the entry section where it first checks the lock variable. If the lock variable is 0, it sets the lock variable to 1 and enters the critical section. After executing the task in critical section, the process enters the exit section and sets the value of lock variable back to 0. But if the value of lock variable is 1, the process is sent to the waiting queue, where it waits for the other process to empty the critical section. The process in the waiting queue are then invoked when some process exits critical section and sets the test variable to 0. Fourth, turn variable. It is also known as strict alteration approach. It is a software mechanism implemented at user mode. It is a busy waiting solution which can be implemented for two processes. A turn variable is used, which is actually a lock. It is shared variable between two processes. The first process that the user will click upon will set the turn variable and enter the entry section. The entry section is responsible for checking if the value of turn variable is equal to the process name. If the value of turn variable is equal to the value of process clicked, then the process will enter the critical section, and if they are not same, then the process will enter the waiting list. Once the process in the critical section completes its execution, it enters the exit section and alters the value of turn variable, and then invokes the process in waiting list to complete its execution. Fifth, Paterson's algorithm. It is a software-based solution. It has two shared variables for interest and turn. It is a solution for mutual exclusion, progress, and bounded waiting, as only one process is allowed in critical section, and every process gets a fair chance and no process blocks other process from entering critical section. In this algorithm, the first process that the user will click upon will enter the entry section and set the value of turn variable and set the interested variable for the process to true. The entry section checks if the value of turn variable is equal to the process number and the value of interested variable for the other process is equal to true. And then the click process will enter the waiting queue. Otherwise, the process enters the critical section. After the process completes its execution of critical section, it enters the exit section, setting the interested variable for that process to false and invokes the process in the waiting queue to complete its execution. Sixth, binary semaphore. They are also known as mutex locks as it provides mutual exclusion. This type of semaphores have their value restricted to 0 and 1. The value of semaphore is initially set to 1. When a process is clicked, it enters the entry section and checks the value of semaphore variable. If the value of semaphore is 1, then the process enters the critical section setting the value of semaphore to 0. Whereas if the value of semaphore is 0, then the process goes into the block state. Once the process in the critical section completes its execution, then the process enters the exit section and alters the value of semaphore variable to 1 and wakes up the process in block state to complete its execution. 7th, counting semaphore. It is an extended version of binary semaphore where the value of semaphore variable is not restricted to 0 and 1. Thus, they can be used to control access to a resource that has a limitation on the number of simultaneous access. In this algorithm, the user is asked to enter the number of processes and the maximum value of semaphore variable that they want to consider, and then press the start button. When a user clicks on a process, it enters the entry section and checks the value of semaphore variable. If the value of semaphore variable is greater than 0, then the process enters the critical section, decrementing the value of semaphore variable by 1. Whereas, if the value of semaphore variable is less than or equal to 0, then the process enters the block state. Once the process in the critical section completes its execution, it enters the exit section and increments the value of semaphore variable by 1 and wakes up the process in block state to complete its execution. 8th, producer and consumer's problem. It is a classical multi-process synchronization problem. There is one producer and one consumer. Producer is producing some items until buffer is full, whereas consumer consumes the item until buffer is empty. They share same memory buffer which is of fixed size. Both cannot access the memory buffer at the same time. In this algorithm, the user is first asked to input the maximum size of the buffer space that will be accessed by the producer and consumer. The producer will then produce items on the click of producer button until the buffer is completely occupied. Once the buffer is full, it will show an alert displaying that the producer can no longer produce items. The consumer will consume items on the click of consumer button until the buffer is completely vacant. Once the buffer is empty, it will show an alert displaying that the consumer can no longer consume items. And last, dining philosopher's problem. In this problem, there are 5 philosophers sharing a circular table and they eat and think alternatively. There is a bowl of rice for each philosopher and 5 chopsticks. A philosopher needs both their right and left chopsticks to eat. A philosopher may eat if they are both chopsticks available, else puts down their chopstick and begin thinking again. In this algorithm, the user will first have to enter the sequence in which the philosopher will eat and click on the eat button. The algorithm checks the availability of resources for all the philosophers in the order provided and then allocates the resources to the philosophers for which both the left and right resources are readily available in the given sequence. Once philosophers are done eating, they will free up the allocated resources and algorithm again executes the entire process until all philosophers are done eating. Thank you.